For this review of electron configuration, I would hope that you can have a periodic table with you as well as your off-bow principle. So unfortunately my video is not big enough, the video area is not big enough to have that out, but it would be great to follow along with it on the side with us. So I do have my periodic table here on my other phone. So let's get started. Let's start with the orbital box diagram. So we're going to represent each of the orbitals with a box. And so in terms of silicone is here, it's number 14. So we need to place 14 electrons. And we're going to be first putting 2 down in the 1s2 orbital. Then there's going to be a 2s orbital. We'll see our 2p orbitals. We'll put 1 in every box, and then we'll go back to fill. So every orbital gets 1 before we get paired up. And so just to kind of follow along on our periodic table, we filled the 1s orbitals, we filled the 2s orbitals, we just filled the 2p6 orbitals, 2p orbitals, and now we're on to 3s orbital. Great. And now we're into 3p. That's the electron for aluminum. And then silicone, again, we're not going to pair it up. We're going to make sure that they're in separate orbitals. Again, you could have followed along with the off-bow principle, and that's going to be particularly important now as we go to bromine. Bromine, it has 35 electrons to place. So we're going to... I'm just going to kind of copy what I have up top here. That brings us all the way to argon. So we've got 18 electrons here. So following the off-bow principle, after the 3p orbital, we would be going back up to 4s. And then once we fill those two 4s, the 2 electrons in the 4s, the next block that we go into is the 3d orbital, which you can follow along on your off-bow. So 3d, the d orbitals have 5 orbitals, so we want to show that here with 5 boxes. Again, you would put 1 in each one first, and then go back through to pair them up. So that takes care of 3d10. And then we're going to have 1, 2, 3, 4, 5 electrons in the 4p orbital. 1, 2, 3, 4, 5. So typically we would be calling this ground state electron configuration. These are not excited state. There's no extra energy being put in here. There's no electron promotion happening. And so if we want to kind of represent this, rather than using arrows and boxes, we can use the names of the orbitals and describe like how many electrons are in each of the orbitals. So for silicone, we wanted to place 14 electrons. So we'll put in the 1s orbital, we'll put 2. That's that box. This one is the 2s orbital. Again, we'll put 2. Here we had the 2p6 orbital. 6 electrons inside the 2p. 3s, 2. And then inside the 3p orbitals, we only have 1, 2 electrons. So we will just put a 2 up there to represent that. So for the bromine, again, we're going to follow 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p, 1, 2, 3, 4, 5. A lot of people will also stick to the off-bow principle chart to help them get themselves off the ground. And as you do more and more of these, you'll start to have like anticipate some of the bumps in the road, some of those twists and those turns, and you'll just start to memorize this basically the more that you do. So Tallium is a particularly tricky one. It's down here at 81. Okay, so it's way down here. And it's important for me that we take a look at that because we're going to integrate in our F orbitals. So we have S, D, P, and then these guys at the bottom are F orbitals. There are 7 of those F orbitals, and each orbital takes 2 electrons. So, and we remember how it sort of fits in here. And we have to sort of follow our off-bow to see how does that actually fit in. So, with the Tallium, we can go all the way up to where we were here with bromine at the very least. So let's take ourselves here to krypton. Then we're going to go down into the 5s2. Again, just follow along on your off bow. So 5s2, then 4d10, 5p6, 4d10, 5p6. We exit 5p6 into 6s2. And then as we go out from 6s2, we're going to enter into 4f. And you can notice that on your off-bow principle. From 6s, it goes right into 4f. And keep in mind that the f's are 14. If you go all the way across. The d's are 10, so 10 electrons inside 5 orbitals. F's are 14 electrons inside 7 orbitals. So we go 4f14. And then 5d10. Whoops. Good catch. And then finally we get right out of that transition metals. And here we're at 6p1. That's not very fun at all. And so let me show you one way to sort of ease this pain, if you will. What we want to do is called a noble gas configuration. So we want to go back to the last noble gas, the last spot where all the electrons have filled all of the orbitals. So for silicon, the last noble gas, this is silicon. If we go back, sort of back along the periodic table, neon is the last noble gas with 10 electrons. So we could see here 6, 2, 2. This is all neon. So if we were to write an abbreviated noble gas configuration, we would put a square bracket and then Ne. And then we would start to build the silicone configuration after Ne. So every chemist knows the configuration of neon. So now let's build it from there. So 4 whoops, not 4, 3. 3s2, 3p2. So I'm just going to take us back here. We could see that it's these guys that are sitting there. So neon and then everything else after. For bromine, bromine has argon as its previous noble gas. So we're, again, going backwards from 35, drill it all the way back to the last noble gas, argon. And argon sits up here. The last electron that gets placed for argon is the 3p6 electron. So these guys all become part of my noble gas configuration. Square brackets for argon, then it's 4s2, 3d10, 4p5. And Tallium, down here with 81, if we go back, should look like xenon. And xenon goes all the way to the 5p6. Look at all that we get to save. We don't have to write them all the time. My goodness. Oh, goodness. So, in terms of noble gas configuration, we're just going to write these guys out. Great. I think I'm good with this now. So one other thing that, we can talk about, which is, if you ever hear the word, right, the abbreviated electron configuration, that's the same as noble gas configuration. But the valence configuration is not the abbreviated. Valence configuration does not show the noble gases. It just shows the electrons in the highest energy level. So for silicon, our valence configuration would simply be 3s2, 3p2, because these are in the third quantum level or the third energy level. For bromine, our valence configuration would be 4s2, 4p5, and we would ignore the 3d10 because that's in the third energy level. For Tallium, it's just 6s2, 6p1. So again, ignoring all the other things. This is the valence configuration, electrons in the outermost energy level. We can also show electron configurations for ions. So bromine, and again, maybe it's easier for us to look at the orbital box diagram. But for bromine here, when it forms an electron, or an ion, we can either give or, so give meaning lose, or we could gain by getting. So do we want to lose 5? Obviously not. We want to gain. We just want that one more electron here. If we can get that, then all the orbitals are full. We're going to achieve that stability. So we want one to be up one electron. And currently we're at 4p5. So we really want to look like that next noble gas. So electron configuration for ions, I'm just going to abbreviate it. No, I will not. I will do the full configuration. So again, follow along on your off-bow principle if you need to. So normally we would have 5 electrons, but because we're up 1 electron, so 35 protons, I believe. Yeah, 35 protons, we're going to have 36 electrons. So this will be 4p6. So it'll be one more than that. The strontium ion, so strontium's here at 38. Strontium's going to form a +2 ion. And if we go back to our previous unit, we ask ourselves, what does that mean, a +2? That means that it's going to lose 2 electrons. So normally we would be showing 5s2 for strontium, but because it's going to lose these 2 electrons, it will look just like krypton, which in fact looks just like the bromine ion. So normally, again, we would have that 5s2, but because it's the cation, it's going to lose those 2 electrons. Whereas the bromine gained 1 electron because it normally has 4p5. The last thing that I want to definitely include is your exceptions to the rules. Of course, those transition metals are going to give us a hard time. So I want to take a look at silver, and we can use the abbreviated form for silver. So normally, we would go back to krypton and start to build up. And normally this would be our configuration for silver, being 47. So we would be talking about the 5s2 and then 4d9. Now, in terms of the orbital box diagram, if we look at the Ds, there's 5 orbitals there. And if we're thinking about placing 9 electrons inside there, there's 5, 6, 7, 8, 9. There's literally like 1 electron. It's like wobbly now. If it could only get 1 more electron here, then it would be completely stable. And so what this does, what silver does, is it actually takes 1 from the S's and moves it up to make the 10. So this guy becomes a 1. So rather than having a paired electrons in the S's, it allows the D's to be completely paired up. So so the full electron configuration for silver would be 5s1, 4d10. And just be really careful as you're looking online for assistance on these. There's a lot of like inaccurate websites, and usually it's like forums where people are talking about configuration and they're not right at all. So just be careful. I think some people on Friday nights, they go on those things and they start typing in wrong answers just to mess up first-year chem students. So hopefully you don't get caught up in that. The other one I wanted to look at was number 42. So again, this guy, if we just use the noble gas configuration for it, 5s2, 4d4. And in terms of the orbital box diagram, this one would look like arrow, 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 and there would be nothing left in this one. Again, kind of wobbly, super unstable. It's going to promote this electron here so that 1 electron is in every one of the d orbitals. And there's 1 electron also in the s. So just keep your eye open for 44 and 49, because those guys don't really want to be leaving one spot open. They would rather have everybody all spread out nice and even. So they will try to steal and sneak one away from the S's. Whew.